Hello and welcome to the Absolute State of Science Part 0. This is a video series presentation that takes place inside of virtual reality, and the things that I'm holding in my hands here are part of the program. They are effectively my paintbrush or sculpting tools that I use to manipulate art in three-dimensional space. So as you can see here, that's all this is. But that's not what we're going to be talking about. This has nothing to do with art. We're going to be talking about science. In this episode, we're going to talk about the theoretical physics that were used in the film Interstellar and where they came from and why. So what's so great about the film is that it, I feel like, really successfully portrays the inside of a wormhole, a black hole with an accretion disk, and the effects of time dilation. So it's not all science fiction, despite it being part of the sci-fi genre. It's actually a lot of science fact. The CGI model of the black hole for Interstellar, based on calculations by Kip Thorne, right here, this guy, The Science of Interstellar, Kip Thorne. So here's Kip Thorne with the Hawkster. The model is thought to be the most accurate depiction of a black hole ever. Why that is such an impressive feat is because we've never actually observed any of these things. We've never seen a black hole or a wormhole. We can't see these things. They are theorized to exist. So these three things actually come from a field of science called theoretical physics. As it is right here, it's a branch of physics that employs mathematical models and abstractions of physical objects and systems to rationalize, explain, and predict natural phenomenon. So what it means by predict natural phenomenon, for example, we have over here, visual representation of a Schwarzschild wormhole. Wormholes have never been observed, but they are predicted to exist through mathematical models and scientific theory. It's how we think space and the universe works, because we're not sure. Because when we look up at deep space, we don't have anything in deep space. We don't have any satellites out there. All we can do is sort of look at it and then guess based on what we see. And the other insanely cool thing that they successfully captured in the film was time dilation. The way the astronauts age in the movie due to time dilation was accurate. Wait a second. What? So like if you're close to a black hole, time affects you differently? And the fact that time has anything to do with gravity is just, like, that's so hard to comprehend. It's such a difficult concept for me to wrap my head around. Like, who came up with the idea of time dilation? Who came up with the idea of a black hole? Wormholes? Who came up with that? Where did that come from? So all of these ideas actually come from Albert Einstein and his general theory of relativity, which has been described as the most beautiful of all existing physical theories. And the theory has been such a success that it is categorized under the mainstream theories or the central theories. It's a really big deal. Why do they think that way? Like, why do they think that space and time are the same force? Why is that a mainstream theory? I only ask, the only reason I'm even asking that is because whenever I look at the night sky, I've never seen anything that looks like a wormhole. And so why do they assume that there's a wormhole there? I mean, like, I'm not saying it isn't there, I've never seen one, and they admit they've never seen one either. So why do they assume that? You know, I need to see some evidence here to your claims. I'm gonna go all Carl Sagan on you here. The Sagan standard. Extraordinary claims require extraordinary evidence. Well, how about this for some evidence? In 2015, the LIGO project was the first to directly observe gravitational waves using laser interferometers, matching predictions of general relativity. Observing to date no deviations from theory. So LIGO is not the first, it's actually the last in a long line of evidence we've found that supports general relativity. Well, that's cool, we have some evidence. What does evidence have to do with science? And that brings us to the scientific method. Every baby knows the scientific method. The first thing they do is they use their senses and they say, oh, look, a little green ball. And then they form a hypothesis, which is a synonym for a theory. The baby says, I think it's food. That's my hypothesis. And so he performs a testable experiment and he pops it into his mouth to see if it's food. And he analyzes the data, and he says, oh no, that's absolutely not food. He screams and says, hey guys, my hypothesis that this green ball is food is wrong. So then he invites others to reproduce their results. I'm pretty sure it's not food based on my experiment. What do you think, other baby? And so thus, that is the scientific method in a nutshell. So now that we have a general understanding of the scientific method, let's look at how we arrived at time dilation and the visual effects seen in Interstellar. It all stems, really, from Albert Einstein's theory of general relativity. Is one of the towering achievements of 20th century physics. Published in 1916, it explains that what we perceive as the force of gravity in fact arises from the curvature of space and time. Einstein proposed that objects such as the sun and the earth change this geometry. Wow, that is a really complicated thing. Let's look at how he figured that out. So, Albert Einstein was, of course, a genius scientist and former baby, so he knows the scientific method really, really well. So he got together with his old teacher here, Hermann Minkowski, right? And they looked at all the observations that we had. So they looked up all the work of Newton and all the work that we had on gravity and all the measurements, all the observations available to them at the time. And they say, you know, speaking of the time, it is 1916. Do we know how time works yet? And everyone sort of looks at each other and says, no, actually, we have no idea how time works. So we have all of these measurements about space, but we don't really have any measurements about time. Hey, here's an idea. What if space and time are the same thing? And so Einstein and Minkowski here, they worked together, and they came up with the idea of combining the two, and they did this mathematically, so you know it's accurate. Minkowski spacetime is a combining of three-dimensional Euclidean space and time into a fourth-dimensional manifold. So they came up with that idea, which is very cool. Here's kind of what it looks like. Very mathematical, very complicated. They come up with their hypothesis, and after the hypothesis, as we just learned, the next step is to test your hypothesis by doing an experiment. Minor problem, though, with their hypothesis. It can't be tested. Instruments can neither see nor measure spacetime, so they have no direct way to do it. And Einstein says, oh, right, so about that experiment, how about instead of a normal real-world experiment, hear me out, let's do a super cool new idea called a thought experiment, where we don't need any physical evidence. How about that? So the entire idea of time dilation comes from a thought experiment and not a real experiment. And they're like, no, Einstein, it has to work. The whole point of doing a test is that it's an investigation of whether the real world behaves as predicted by our hypothesis. So we have to know that the real world behaves this way. And he's like, okay, fine, I can't use thought experiments. Well, then I predict that the real world is going to behave like this. I predict that on the next solar eclipse that you see, light will bend in a gravitational field. Is that good? Is that good enough for you, scientific community? And that's exactly what happened. The solar eclipse of May 29th, 1919. During a total solar eclipse, Sir Arthur Eddington performs the first experimental test of Albert Einstein's general theory of relativity. The findings made Einstein a celebrity overnight. And so that is why Einstein is a huge celebrity and is synonymous with the word genius. Because he said, I'm going to do some math out, I predict space and time are the same thing, I predict light is going to bend, and then it did, making everything he said correct, which means space and time are the same force and life is great. And after Einstein predicted a warping effect, everyone goes, cool, let's publish it in all the books and teach everyone about it until the end of time. And space. Whatever, I'm not sure how that all works now. Albert Einstein's general theory of relativity is one of the towering achievements of 20th century physics. It set the whole scientific paradigm for how we look at space. It's been great. It has predicted so many things. From 1916 forward, we kept seeing phenomenon in space that matched predictions made by Einstein. So every galaxy that we saw matched perfectly. But then, in the 80s, something weird happened. So something, a little something happened in 1980, not really a big deal. We found a galaxy that doesn't match. It's an SC galaxy. It's doing a weird thing and it doesn't match Einstein's prediction at all. So let's look at this paper, published in May of 1980. Rotational properties of 21 SC galaxies. SC galaxies of all luminosities must have significant mass located beyond the optical image. So that means that galaxies shouldn't be moving like that unless there is invisible stuff that's making more gravity. So more mass equals more gravity. This just needs a little help from an invisible matter. The observed trajectories of stars turn out to require more galactic mass than our telescopes can detect. Dark matter. Invisible dark matter makes up most of the universe, but we can only detect it from its gravitational effects, which leads scientists to believe that something we cannot see is at work. They think something we have yet to detect directly is giving these galaxies extra mass, generating the extra gravity they need to stay intact. This strange and unknown matter was called dark matter since it's not visible. So let's run through this with our newfound scientific method. The first thing the scientific community did was they made an observation. Okay, we found SC galaxies that don't match the theory. This is the first observation to not match the theory that we've found in 60 plus years. Let's come up with a hypothesis. How about dark matter? Maybe dark matter is there, but we just can't see it. So to prove that the invisible or dark matter is there, the scientists at CERN, the European Organization for Nuclear Research, built the Large Hadron Collider, the LHC, the world's largest particle accelerator, in order to prove their theories. Let's hold on a second. There's one small problem with their hypothesis. They kinda did something that you're not really supposed to do. Yeah, it's actually an ad hoc hypothesis. In science and philosophy, an ad hoc hypothesis is a hypothesis added to a theory in order to save it from being falsified. An example of that would be if someone wants to believe in leprechauns, they can avoid ever being proven wrong by using an ad hoc hypothesis. Example, by adding they are invisible, then their motives are complex, and so on. So you can keep making up reasons for why things don't fit your initial hypothesis. And that's actually called a logical fallacy, which is a flaw in reasoning, something that weakens or destroys an argument. So the logical fallacy committed by the scientific community is special pleading. You moved the goalpost or made up an exception when your claim was shown to be false. Let's look at this one again. Let's look at this one piece from this paper. For decades now, numerous cosmological observations have suggested the presence of a large amount of excess matter in the universe, of unknown composition. What kind of observations are we talking about here? Let's just look. Let's do a little look in here. Oh, look, this is the bucket of things we will figure out later. It's also a bucket of evidence that falsifies the original theory. We're gonna jump into this bucket. If you want to view paradise, simply look around and view it. Want to change the world? There's nothing to it. Dun 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 dun. Dun, dun, dun. And all of this is magically explained if dark matter is there. You find dark matter, bam, all this makes sense. Perfectly logical. How are the experiments going? You guys able to detect it? Oh, no. The world's most sensitive dark matter detector, complete search, but yielded no trace of the dark matter particle. But if you're a scientist, you're gonna have to be willing to let your beliefs go. Uh-oh. Dark matter hunt fails to find the elusive particles. Uh-oh. We do not understand how the universe works at a deeper, more profound level than most of us care to admit. Uh-oh. Hunt for dark matter. The results essentially send physicists back to the drawing board. Oh no. They can't find it. The Chinamen can't find it either. No dark matter signal was observed for the first Panda X run. They have no idea. Also, the Large Hadron Collider has not found any dark matter either. And so this is David Tong speaking at the Royal Institute.
The reason that we built the LHC was firstly to find the Higgs, okay, it worked, and secondly to test these kind of ideas that we've been having to see what lies beyond. So the LHC has been running. It's been running for 2 years. It's been running like an absolute dream. It's a perfect machine. 2 years, this is what it's seen. Absolutely nothing. Okay? All of these fantastic, beautiful ideas that we've had, none of them are showing up at all. And the question going forward is, what are we going to do about it? How are we going to make progress in understanding the next layer of physics when the LHC isn't seeing anything and our ideas just don't appear to be the way that nature works? So my response is, I think that maybe we should just go back to the drawing board and start to challenge some of the assumptions and paradigms that we've been holding for the past 30 years.
Paradigm provides the underlying structure upon which is built the subsequent research. That means the way we've been viewing space since 1916 is based off of general relativity. He suggests we go back 30 years and challenge the way we view things. I'm going to take it one step further. What if we goofed? So what if the first piece of evidence that set us into thinking that space and time are the same force has an alternative explanation? This is what our telescope sees, and this is a hypothesis, a theory, how we think all of that works. We're supposed to test our hypothesis by doing an experiment. He couldn't do an experiment, so he did a prediction. His prediction turned out to be right all the way up until it turned out to be wrong in the 80s. Now, 100 years later, we have found a ton of things that say the real world does not actually behave by your predictions. So, experimental evidence. Although instruments can neither see nor measure space-time. Holy shit! This paper is an alternative explanation that says, mathematically, it could be the refraction of light, and not space and time. If it can't be tested, then your theory doesn't have much value. One of the pillars of physics, the pillars of modern physics, and perhaps the most revolutionary theory in the history of physics, has an alternative explanation, thus rendering the first piece of evidence we ever collected on it null and void, relying only on thought experiments, meaning we have no reason to assume that space and time are the same force. We have no reason to assume that because we have no evidence that suggests that. And it's wrong! It didn't predict. There's a whole bucket of slop that it doesn't predict in its native form, meaning it's wrong. It's wrong. It's falsified. It's wrong. And you already pushed past the boundaries. You moved the goalpost with special pleading and ad hoc fucking bullshit, and then spend $6 billion, 530 million of American dollars on this stupid fucking nonsense bullshit. And of course that's coming up wrong because the whole fucking thing is wrong. And he goes, because we're detecting things in 2015 that match the predictions of general relativity. Another thing you gotta worry about in science, this is pretty cool, it's called beliefs and biases. So, for example, pre-existing beliefs can alter the interpretation of results, as in confirmation bias, that leads to a person with a particular belief to see things as reinforcing their belief, even if an alternative observer might disagree. In other words, people tend to observe what they expect to observe. You don't seek to prove scientific hypotheses right, you only prove them wrong. When we begin to test a theory, are we looking to confirm or disconfirm? That is how you do science. Science! What does it say? Study of the physical and natural world through observation and experiment. In a pillar of modern physics, you have neither. So critical thinking. The scientific method relies on critical thinking, which is the process of questioning common beliefs and explanations to distinguish those beliefs that are reasonable and logical from those which lack adequate evidence or rational foundation. Hold on, let's pump the brakes. So we have one theory saying that it's space and time bending, and we have another theory saying that it's refraction of light. Before we jump into all that, let's just do a little bit of the scientific method. The traditional understanding of the scientific method, to look at the world with a scientific eye, is to observe with no preconceived notions. So let's just look at space. Let's just do it together. What do I see in nature? Lights, I see lights, I see light-producing objects. What are all the things that produce light? Well, the sun, that's a pretty big one. Okay, so we know that the sun and very hot things that are very hot, produce light. Electricity and all electrical things, they produce light as well. The plant and fish things, they produce light. And then the last one is the northern lights. I don't know what those are, but it's a bright light that appears in the atmosphere. Those are all the natural things I can think of that produce light. Let's start with the hot things category because we know that it exists in space. Well, what is the sun made out of? The sun is composed of plasma. I thought the sun was a nuclear fire. Fire is plasma. Okay, good, that settled that. Plasma is not a gas, liquid, or solid. It is the fourth state of matter. Plasma often behaves like a gas, except that it conducts electricity and is affected by magnetic fields. Hold on. So that means that the sun, which is made of plasma, conducts electricity and is affected by magnetic fields. To test that, we have fire. So since fire is a plasma, does fire conduct electricity? Let's run an experiment. Yes, fire conducts electricity. Electricity is also a plasma. Lightning bolts are plasma. On an astronomical scale, which is what we're looking at, plasma is common. 99% of the universe is made up of plasma. So that would mean that all this stuff that looks like gas is actually plasma, which is why it's making light. So instead of viewing these as very hot fire phenomenons, maybe these are very hot electrical phenomenons. Oh, what's that? Universe's highest electric current found? How magnetism manifests in the universe? So what about the northern lights? What are those made out of? Supersonic plasma jets discovered in Earth's upper atmosphere, and it shows a picture of the northern lights. So the northern lights are glowing plasma as well. Northern lights caused by electrical tornadoes, scientists discover. So electrical tornadoes. Are all tornadoes electrical? Well, let's look. A waterspout is a atmospheric dusty plasma. So a waterspout, which is a giant column, just like a tornado, is also made of plasma and has something to do with electricity. The electrifying dust devils on the surface of Mars. Cosmic tornadoes. So it seems that regardless of the environment, a spinning pillar shape all seems to be related to plasma or electricity in some way. Let's return to our original SC galaxy, and let's compare that to a surface discharge pattern in high magnetic fields. So this is an electrical discharge with a different external magnetic field. And one of the electric discharges happens to naturally make a spiral. Sort of looks like a tornado, which sort of looks like a galaxy, and a galaxy is made of a material that conducts electricity and is affected by magnetic fields. So that actually concludes part 0, but we're not quite done yet. We are going to, we're going to get a little sneak peek from part 3. Part 3, of course, is extraordinary evidence. Why part 3? That's because part 1 and 2 have already been released. They are on my channel. You could check those out. Part 3 should be out pretty soon. So let's just give you a little sneak peek. Dust devils have an electrical heartbeat, and they physically morph the surface of Mars. So here's what some of that looks like. Those are from dust devils. The spirals on Mars line up with the spirals on a galaxy. So the shape of a galaxy lines up with a spiral on Mars. What's even cooler is that if you take an electrical arc and shoot it into a magnet, it produces a really similar shape to the spirals on Mars as well. That's just a little snippet from part 3. So yeah, you should subscribe, click the bell. It's going to be great, and thank you for watching. I appreciate it.